So let's see the next problem. As we can see, the function is very nice, a polynomial function, and the domain is given by these inequalities. The first thing is we are going to sketch the domain. The conditions that x and y are greater than or equal to 0 gives us that the region is in the domain, is in the first quadrant. Okay, this inequality, from this inequality, we have the equation is nothing else that y is 1 minus x, that is an equation for the line intercept here, intercept here. Okay, to figure it out, since this line divides the plane into two parts, we have to figure it out which part satisfying the inequalities. X plus y is smaller than 1. So let's just pick a test point, 0, 0. Substituting back, 0 plus 0 is 0, which is clearly smaller than 1. So this region under the line satisfying the inequalities, it means that the domain is gonna be this triangle with the sides as well. Okay, here. That is, the domain is bounded and closed, which means that the function, which is clearly a continuous function, takes its extrema. Okay, maybe inside of the domain region or on the perimeter. Okay, so let's see, do we have critical points inside or not? To get that one, we have to calculate the partial derivatives. Okay, 3x squared plus 2xy. This is the partial derivative with respect to x, and with respect to y is gonna be x squared plus 4y. To get the critical point, we have to solve the following systems of equations. So from the second one, we can see that y is minus x squared over 4. Plugging back into the first one, we will have 3x squared plus 2x times minus x squared over 4, which is 3x squared plus, minus x cubed over 2. Okay, we have to show that this one is 0, so let's just factor out x squared over 2 to have 6 minus x. Okay, we will have this product is 0 when x is 0 or when x is 6. But when x is 0, from here we will have that y is 0. When x is 6, okay, 36 divided by 4, 9, so y is gonna be minus 9. Okay, let's see, where are these points? Okay, 0, 0 is here, okay, not inside of the region, of the domain, and this one 6, x is 6, y minus 9, somewhere here. Clearly this one is outside of the region, so we don't have any critical points inside of the region. Now we have to consider the boundary of the region. Clearly this is the right triangle, so very likely, not likely, we must calculate the function value at the vertices. Okay, so we have 0, 0, okay, this vertex. The function takes the value, okay, clearly 0, and here at this point we have, this one is 1, 0, the function value is 1, 1, and here the last vertex is gonna be 0, 1, so here we have 0, 0, so that one is 2. Okay, so Obviously, we could have a minimum maximum here. So here 0, here we have 1, and here at this point the function takes the value 2. Okay, but besides these points, we can have critical points inside of these, okay, sides, okay. So we have to consider the 3 sides separately. So let's just see what we have first, okay. So this is the side when clearly the x value is 0 and y runs from 0 to 1. So the function is gonna be fx. Y is, we can substitute 0 for x, 0 y. So that gives us nothing else but 2y squared. Okay, this is a function of one variable, and clearly we can draw the picture of the function of 2y squared. Okay, be careful. Okay, the horizontal axis is gonna be the y-axis. Okay, so this is the graph of the 2y squared. But we have a condition that y runs from 0 to 1 only, so we don't have to consider these parts. So we have just only this one. Clearly between 0 and 1 we don't have any critical points, minimum, maximum, and of course we are already considered the vertices, okay, which are corresponding to these points. So no more point we have to take there. Okay, second side, in this case y is 0 and x is between 0 and 1. So in this case the function on this line segment is gonna be, okay, x runs from 0 to 1, but y is 0, so plugging back 0 for y, we have x cubed. Okay, again this is a function, clearly we know the picture of this one, something like this. Okay, the x cubed function. Okay, but the condition again that the same, that x just between 0 and 1, so it means that we just have to consider this part of the function, and clearly inside between 0 and 1 we don't have any special points, so again we don't have to pick any point between 0 and 1. Okay, and on the third side, in that case we have, oh yeah, this is the line segment, so we already know that okay, x could be anything between 0 and 1, and y is the 1 over x. So the function f of x, y is nothing else but f of x 1 minus x, plugging back 1 minus x for y, x cubed plus x squared, 1 minus x plus 2 times y squared is 1 minus x squared, gonna be, so what we have here, x cubed and minus x cubed plus x squared and plus 2x squared minus 4x and plus 2. Okay, let's see, this can cancel out each other, so we have combining the similar terms, 3x squared minus 4x plus 2 function. Okay, of course we could draw the picture, like correct picture of this quadratic function, but it's enough for us to see that this one is a smiling or smiling face, right? Because minus 3, the coefficient of x squared is a positive number, and we know that this point, the minimum point, is minus b over 2a, well this is a, this is b, so that is gonna be 8 over 6. But since we have the condition that x is between 0 and 1, this one is clearly bigger than 1, okay? And very likely, because this one is bigger than 1, on this line segment, the function looks like this one, okay? So clearly, again, besides the vertices, there is no point we have to consider. So this is a very simple problem. We have just only 3 numbers, and we have to pick the smallest one, which is clearly 0. So on this region, on this domain, the global minimum of the function is 0, and clearly the maximum is gonna be 2. That's it.